So now let's look at Newton's second law. The second law says that the net force acting on a mass causes the mass to accelerate. So with Newton's first law, we had sum of all forces equals 0. But with second law, we have sum of all forces is equal to mass times acceleration. When Newton wrote this, he actually wrote it in a different format. He said the acceleration of an object is equal to the sum of all forces divided by the mass. The reason he did that was twofold. Number one, he wanted to show that as you increase the force or the net force on an object, then the acceleration would go up. He also wanted to show, though, that mass resists acceleration. We talked about that with inertia. We said the more mass you have, the more its inertia, and the more its inertia, the more its resistance to change in motion. Well, what's change in motion? Change in motion is acceleration. So he also wanted to show that as your mass went up, your acceleration went down. We would say that if we had a situation like an increase in force equals an increase in acceleration, that they are directly proportional, meaning when one goes up, the other goes up. And then if we look at an increase in mass causes a decrease in acceleration, we would say that those are indirectly proportional, because when one value goes up, the other goes down. Now, this also helps to explain why everything actually accelerates at exactly 9.8 meters per second squared on Earth. Think about it. If you have a bowling ball and you have a beach ball, and you want them both to accelerate at exactly 3 meters per second squared. So you want acceleration for both to equal 3 meters per second squared. Well, your bowling ball has a bigger mass, so a big mass. Put a big M up there for the mass of the bowling ball. The mass of your beach ball is much smaller, so put a little bitty mass. Acceleration is going to stay the same. So in order to get the mass of my bowling ball, or my bowling ball to accelerate at 3 meters per second, and my beach ball to accelerate at 3 meters per second, what do you have to do force-wise? Well, obviously, you're going to have to push harder or with a greater force on the bowling ball and not have to push very hard at all on the beach ball. And in each one of these cases, you're going to get the same acceleration. How? Well, let's write it out. We would have acceleration, which is going to stay the same, is equal to a big force over a big mass, right? Or we could say our acceleration is going to stay the same. It could be a little bitty force over a little bitty mass. Or you can even put numbers in. You could say you push with 300 newtons of force on 100 kilograms, or you could push with 3 newtons of force on 1 kilogram. In each one of those cases, you're going to get an acceleration of 3 meters per second squared. We had to push harder on the object with more mass. We didn't have to push as hard on the object with less mass. That's exactly what happens with the Earth. The Earth pulls harder on objects that have more mass and less hard or with less force than on objects that have less mass. So if you take Galileo's little experiment on Leaning Tower of Pisa, here he is. He's going to drop his two objects. There's one, and there's the other. We'll say that's 3m, and that's m. To get these to accelerate at 9.8 meters per second squared, Earth has to pull with 3 times the force that it pulls on the lighter object. And if that was 5m, it would pull with 5 times the force to get it to accelerate at the same value as, say, mass. And 1/4. So that's why everything accelerates at 9.8 meters per second squared. The other thing I want to talk about with Newton's second law, again, is just to kind of cement into your brain what weight is. Weight is a force. Make no doubt about it. Weight is a force. It is not a mass. If you get an equation, or if you get a problem that says find the force of 3 kilogram mass, then you don't write 3 kilograms as your answer. What you have to do is you have to plug it into this formula. The basic formula of the sum of all forces is equal to mass times acceleration. When we talk about weight, we can change that up just a little bit, and we can say weight, which is really a force, equals mass times the acceleration due to gravity, which is an acceleration. So this formula is the same as Newton's second law formula. They're the same formula. We just are talking about a special circumstance, and so we've changed our variables to reflect that special circumstance. In my opinion, I don't really remember weight equals mg. I usually just fall back with force equals mass times acceleration. But many students prefer weight equals mg just so they can cement that into their brain. Also, if you're going to use mg for your free body diagrams, you need to say mg. You don't say ma. You need to let me know, or if you're an AP, you need to let the AP reader know that you understand that that acceleration is the acceleration due to gravity, and it's that acceleration that's creating the weight of the object combined with its mass. So if we have an object that is 3 kilograms and we multiply that by the acceleration due to gravity, feel free to be lazy and use 10 meters per second squared, then we would know that our weight is 30 newtons. So kilograms, newtons, they're not the same thing. Kilograms refers to mass. Newtons refers to weight. So pay attention to your problems and pay attention to whether or not you're dealing with forces, in which case you would need weight, or whether or not you're dealing with something that would require just the mass. So again, please pay attention to that. Now let's look at free body diagrams in relationship to Newton's second law. Now with Newton's first law, we had to have our arrows pointing in opposite directions and equal and opposite. But in Newton's second law, we don't have to adhere to that because now we are accelerating. Now we would have one arrow longer than the other, or one arrow without a pair on the other side. So we have a ball that's thrown into the air. One of the misconceptions students have about physics would be that when they throw something, that the force of their hand or the force of the throw stays with the object. And that's not true. What actually happens is once that object leaves your hand, then there's no other force acting on it horizontally. The force that would be acting on it in our physics world, which is without air resistance, would just be the force due to gravity. So if we have a ball that's thrown into the air, it's left our hand, we have one force acting on it, and that would be its weight. And its weight is equal to mass times the acceleration due to gravity. That's it. If we wrote this out in formula, we would have the sum of all forces, and if we added up all the forces acting on this, it would be mg, no other force acting on it. But we also know that because this is Newton's second law, that is also equal to mass times acceleration. So now we could say that mass times gravity is equal to mass times acceleration for this particular instance. All right, let's look at a car accelerating to the right. Now, the reason why we do this one is because in this particular instance, we're going to have forces that are acting in the x direction, and we're also going to have forces that are acting in the y direction. So here is my car, and my car has weight, so mg. It's not accelerating vertically, so vertically it's obeying Newton's first law, but it is accelerating horizontally. So in this particular instance, I could say that the sum of all forces in the y direction would equal the normal force plus a negative weight would equal 0, or you could end up saying n equals mg because we could bring that over to the other side. But in the x direction, they don't equal 0. In the x direction, they equal mass times acceleration because we're accelerating. So we would have that push or pull on the car plus a negative friction equals ma. So we could say P minus friction equals ma. Enjoy the video clips. That will help you hopefully understand a little bit more about Newton's second law.
Where was the moment we needed the most? You kick up the leaves and the magic is lost. a smile with the coffee to go. And tell me your life's been way offline. You fall into pieces every time. And I don't need no carrying on. 'Cause you had a bad day, you take it one down. You sing a sad song just to turn it around. You say you don't know, you tell me don't lie. You work and a smile and you go for a ride. You had a bad day, the camera don't lie. You calm me back down and you really don't mind. You had a bad day, you had a bad day. Well, you need a blue sky holiday. The point is they laugh at what you say, and I don't need no carrying on. You had a bad day, you take it one down. You sing a sad song just to turn it around. You say you don't know, you tell me don't lie. You work and a smile and you go for a ride. You had a bad day, the camera don't lie. You calm it back down and you really don't mind. You had a bad day. Sometimes the system goes on the blink and the whole thing turns out wrong. You might not make it back and you know that you could be well, that's wrong. And I'm not wrong. So where was the passion when you needed the most? Oh, you and I, you kick up the leaves and the magic is lost. 'Cause you had a bad day.